Hello, I'm Václav Novotný and welcome to the tutorial of Decentralized Systems 1. This tutorial will be focused on organic Rankine cycle. We will have an example on waste heat recovery, where we will also show the effect of parasitic load. We will show something regarding optimization and effect of adding Recuperator. Okay, so how does organic Rankine cycle, ORC, look from the outside? You can see some examples in here, where on the left we have micro module of just about 2.5 kilowatts of electrical power output, which can be used in waste heat recovery or combined heat and power applications, where this, let's say, box would be connected to hot water of 90 to 120 degrees C and to the electrical power output. Then on the other side of the spectrum is a large organic Rankine cycle for geothermal application, where the net power output is about 4 megawatts, and we can see that those are distinct components as heat exchangers, big piping, other set of some heat exchangers. Between that is somewhere turbine connected to generator and power equipment. But a general trend is to make as much modular and transportable units as possible. So what you can see in the middle is a system with about 6 kilowatts of electrical power output for combustion of wood chips in combined heat and power regime with the 120 kilowatts of thermal output, where this particularly is a system Wave 120 developed by our University Center of Energy Efficient Buildings. But if you look closely at this figure, so the organic Rankine cycle is just this smaller part on the right hand side behind the bulkhead, where the left hand side, the most of this containerized solution is occupied by the space for boiler and fuel handling. Now, how does organic Rankine cycle differ from big Rankine cycle systems, and how does it work? So it's basically an alternative of the big steam systems for either low temperature or low power applications. Same as large Rankine cycles, large steam power plants, its main advantage or main application is external heat source. In the microturbine, or as we will see also further, for example, in internal combustion engines, you combust noble fuels and you have so-called internal heat source, where the flue gas then becomes part of the working fluid. Here you have completely external combustion, and the heat input into the system takes place in some heat exchanger. So the application can be for combustion of solid fuels, waste heat recovery, where you have some stream of water or gas which otherwise could not be utilized, or for example the geothermal application. The power range is rather large, from let's say 2 kilowatts of really micro systems up to several megawatts of large, typically geothermal, low temperature geothermal applications. As the name says, organic Rankine cycle, so the working fluid is organic based, and typically those are either some refrigerants, both hydrofluorocarbons or also alkanes, hydrocarbons can be used, or other working fluids can include, for example, some silicon oil. The whole system is typically hermetic, compared to large steam power plants rather simple, and that is both with respect to configuration as well as to distinct components. For example, expanders, if those are turbines, so they have very small number of stages, or they are even single stage turbines, and in some cases volumetric expanders are used instead because of the relatively low volumetric flows, so this type of expander might be better suited for some of the applications. Talking about the configuration, so let's have a look at the schematics over here, where let's start with the pressurized working fluid after the pump. It can go through the Recuperator, which we will talk a little bit in a few seconds. Then the heat input takes place in component called Evaporator in here, where the liquid working fluid turns into vapor. The vapor is routed to the expander, where it expands and produces power, then converted in generator to electricity. And at the expander outlet, there might be implemented this recuperator before the vapor is condensed in condenser and going to the pump so that the cycle can start again. So now let's have a look at the temperature entropy diagram, where we started in the pump and then we had part of the heat input taking place to the working fluid in the recuperator, then the evaporator, where we have illustrated here the heat source cooling down and our working fluid is heating up. The partly evaporated working fluid then expands in the expander, and this saturated vapor line shows what is so-called dry working fluid. That means if you would have expansion taking place directly from the saturated vapor, you would not go into the wet steam, as would be the case for the water, but you are moving into more and more superheated vapor, further right from the saturated vapor curve. So the superheat might be really small, just for technical purposes to limit droplets entering the expander, so that the expander would not be harmed. Then the expansion takes place to the low pressure isobar. As the expansion ends up in the superheated vapor, so it can be at temperature significantly larger than the temperature after the pump. So that creates possibility of using some of the heat from the expanded vapor to the pressurized liquid over here, and this is the so-called recuperation. Then, when the temperature difference for the heat transfer becomes too small, so the heat is rejected in the condenser. At the end of the condenser, there might be necessary some subcooling, either for net positive suction head for the pump, or generally from the principle that it's unlikely that the last molecule of vapor would just use the last portion of the heat to condense, but the heat transfer in the condenser would work in the way that the end of the condenser would just be slightly subcooled. So let's go to our calculation example, which will be Rankine cycle in application of waste heat recovery. We will have given the heat source, which is specified here as thermal oil of type terminal 66, with given mass flow rate and temperature. Also we have the heat sink, which is air at given relative humidity and given pressure drop across the heat exchangers, so that there will be needed some auxiliary fan for the heat rejection. Then the organic Rankine cycle itself will use MM as working fluid. Now we have given evaporation and condensing temperatures, superheat at the inlet of the expander and subcooling at the outlet of the condenser. We have given efficiency of the components, and pinch point will be same across all heat exchangers in the system, which will be 10 degrees C. And our task is to get not just efficiency of the cycle, but also so-called utilization efficiency, which will be related to the work output of the entire system, and we will relate it with respect to work output of the cycle only. Also we will draw TS diagrams, QT diagrams of the heat exchanger, and we will have a look at some optimization of the evaporation temperature so that the work output can be maximized. And also we will see how adding Recuperator could help us and what effect it would have on the cycle. So let's build a thermodynamic model of our system. First, I've prepared here a table where we have nodes of the organic Rankine cycle illustrated on the diagram over here. We have the pump, after the pump point 1, and then the heat input is divided into 3 distinct sub-heat exchangers: preheater, where the working fluid gets heated up to the saturated liquid level, then the evaporator, where the fluid evaporates, and superheater, where obviously the fluid gets superheated. Then the working fluid is routed into the expander, expands into the 0.5, and as we have shown before on the TS diagram, the working fluid will most likely be superheated, so we have also the heat rejection separated to three distinct subheat exchangers: the superheater, condenser, and subcooler. So therefore we have 8 nodes in here, and then we have 2 auxiliary points, 1S and 4S, which will mark the ideal isentropic state at the outlet of the pump, or respectively the expander. The working fluid is hexamethyl disiloxane. Then for other boundary conditions, here we have efficiencies of our components. Here we have evaporation and condensing temperature, some temperature differences, parameters regarding heat source, and parameters regarding heat sink. So we will start with the model of the cycle itself. So let's put in the first values from the boundary conditions, which are the evaporation temperature, which is the temperature at the point 2, and since it's single component working fluid, so it would be also the same for temperature at point 3. Then we have specified superheating here to be 10 kelvins. So the temperature at the outlet of these heat exchangers for the heat input will be the evaporation temperature plus the superheat. And now for the heat rejection, so we have specified condensing temperature. That would be temperature at point 6 and 7. And we have specified subcooling at the outlet of the combined condenser, subcooler, the superheater. So the subcooling says what's the temperature difference from the saturated liquid point to the subcooled liquid. So it's like this. Now at the points let's say 2 and 3, those points are at the saturated liquid or vapor. So that means that at the point of saturated liquid, the quality of the steam is 0, and at the saturated vapor, the quality of the steam is 1. Similarly, those would be cases for saturated vapor at the point 6, beginning of condensation, quality is 1, and as the condensation finishes, the quality gets to 0 and the subcooling starts. So these are also, let's say, specified inputs, so we can highlight them. Since the property parameters are using basic SI units, so we will convert the temperatures in degrees C to temperature in kelvins. These points 2 and 3, we have specified the steam quality. It's one thermodynamic parameter, and the temperature, second thermodynamic parameter. So for the single component working fluid, this completely defines the thermodynamic state, and we can use these two parameters to get all the other state properties. So let's get the pressure. So to get the pressure, we will use the function props SI, where the output of the function would be the pressure, while the input parameters would be the temperature with the value in here, and quality with the value in here. And the last thing we need to have specified is the working fluid, which is the mm. And let's log this value. So the function goes like this: props SI, output would be pressure with input temperature at this cell, and quality at the cell over here, and the working fluid in here. The same function can be used also for the condensation. And by this we have specified the high and low pressure levels in our cycle. Because we are not considering any pressure drop in the heat exchangers in this example, so we can just copy the value of the pressure into the respective points. So going from the point 2 downstream, it's to the point number 1 after the pump, and then so this is upstream, and downstream from 2 to 3 and 4 all the way to the expander inlet. And now the second pressure, the low pressure in the cycle, is the same from the expander outlet all the way to the inlet of the pump. So just to have the values of the pressure in more comfortable units, let's convert it to kilopascals over here. Like this. So we can see that the cycle, since we want it to operate between evaporation and condensation temperature 150 and 40 degrees C, so it operates between 350 and 11 kilopascals of absolute pressure. Now at the points 2, 3 and 6 and 7, where we have these two thermodynamic properties specified, the quality and the temperature, or now also the pressure, we can use these two parameters also to get enthalpy and entropy. So let's take the same function that we had for the pressure, and just use it here. Now it's the pressure, and the only thing that we will change is the output property, because the inputs are the same. Just use change the output parameters that we want the property function to return. So it would be, we would change it to H as enthalpy, and because we want enthalpy in kilojoules per kilogram, so divided by 1000. Similarly, it will go for the entropy, where the symbol for the entropy is S, so change the H to S, and we get the value of entropy. Now the same function using the temperature and quality can be used also in other points where these two thermodynamic properties are specified. So these 4 points are now given also with respect to enthalpy and entropy. Now let's have a look at the point 4 and 8, because those are the points in single phase where we have provided the temperature and pressure. So in single phase, the temperature and pressure completely define the thermodynamic state, and we can use these two parameters to get others. So let's use the function of enthalpy as a template. So we will still want to get the enthalpy based on temperature. It's still valid, but the second parameter will be pressure. And similarly, it will work for the entropy, where the function will just return the value of entropy instead of enthalpy, and the rest will remain the same. Now the same function can be used also at the point 8, because it's subcooled liquid. Now what are we missing are the points after the pump and after the expander. So first let's solve the point of the ideal pumping or ideal expansion. So let's start with the pump over here. And for the ideal pump with the efficiency of 100%, the thermodynamic change would be isentropic. So that means that for the point 1s, after isentropic change, the entropy will be same as from the point 8. And now we have the entropy, we have pressure, so we can use these two thermodynamic properties to define completely thermodynamic state. So we can use the function here as template. And we still want to get the enthalpy, but now it will be based on pressure. And the pressure is over here, pressure of the high pressure level in the cycle. And the second parameter will be entropy. And we have the entropy over here, but the input into the function needs to be in basic units, joule per kilogram Kelvin, so we need to multiply the entropy value by 1000. And the entropy was here. Okay, so this we get function of the enthalpy, and we can see that the enthalpy increased a little bit. Now you might find kind of confusing or uncommon that the value of both enthalpy or entropy is negative. But for us as energy engineers, it's not the absolute value that matters, but it's always the difference in enthalpies or eventually entropies. And the enthalpy or entropy is defined with respect to some reference point that is arbitrarily given. So the value can go both to the positive values and to negative values, and it's just the matter of the author of the fluid properties functions where they decide to put this reference value. So anyway, now we have done the isentropic change in the ideal pump. Let's do the same with the expander. So again, for the ideal expander, the entropy stays the same, and the enthalpy after ideal expansion will be function of pressure and the entropy. And just now maybe I should call this point 5s, and the pressure, of course, after the expander is already the low pressure side of the cycle. So we can see that the enthalpy for the ideal expander will drop from 291 to 222 kilojoules per kilogram. And now let's convert these ideal values to real ones. So in the real expansion, the enthalpy at the outlet of the expander is the enthalpy at the inlet minus the enthalpy difference for the ideal expansion, the maximum we can get, multiplied by the efficiency of the expander. So the outlet enthalpy from the expander is slightly higher. We don't use all the ideal enthalpy difference we have available, but due to the efficiency we use only portion from it. Now similarly as this, it will go for the pump, but in the pump the enthalpy after the pump is enthalpy before the pump plus now the ideal difference in enthalpies, which due to the efficiency of the pump we need to have higher work input, so this enthalpy difference will be higher as a result of the efficiency. So the enthalpy difference divided by the pump efficiency. And we get that the value after the pump is slightly higher. Okay, and now at these points after the pump or expander, we have given the enthalpy, we have given the pressure, so we can use these two parameters to get the remaining ones, which will be entropy and temperature. So we will get the function for the entropy from here as a template. And now we want entropy as a function of first pressure, where the pressure is over here, and the second parameter will be the enthalpy, and the enthalpy is in here, but again we need to multiply it by 1000, so get the enthalpy is in basic SI units, and at the end we have the value of enthalpy divided by 1000, so that we get value nicely in kilojoules per kilogram. The entropy will be kilojoules per kilogram Kelvin. So we can see that the entropy is slightly higher at the pump outlet, because generally in the pump also the enthalpy difference is very small, as you can see, just about 1 kilojoule per kilogram. And at the outlet of the turbine, the entropy increased a little bit more, from 0.7 to 0.75 kilojoules per kilogram and Kelvin. And similar as the function to get the entropy, we can get also the temperature. So just change the T for temperature based on pressure in here and enthalpy in here, and convert it to kilojoules per kilogram. And convert the temperature from kelvins to, for us, more comfortable degree C. So you can see the temperature after the pump increased just very slightly, around a quarter degree C, and the temperature after the expander is still quite significantly high in the superheated steam, where there is probably considerable amount of heat to be rejected in the superheater. Now we will calculate the mass flow rate of the working fluid in our organic Rankine cycle, so that we can utilize the heat from the heat source within the given boundary conditions and within the given limits. So we will assume that the temperature heat diagrams, the TQ diagrams, will look like what we have here on the right hand side, where first in the top one, let's have a look at the heat input into the cycle, where the working fluid is heated up, then it evaporates and is partly superheated, while the temperature profile of the heat source, there the temperature is gradually decreasing, and we expect the minimum temperature difference to be here between the points 23 and 2. So let's go to our heat source, where we have specified that it's some thermal oil with the type of terminal 66, where in the cool prop we have this fluid among or within so-called incompressibles library or sub-library, and you can see the syntax eventually in this link, where it works that for using the incompressible library, the syntax for the working fluid is incomp T66, like this. Now let's put in the values in the nodes for the heat source that we have here, from 21 to 24. The pressure, well, since it's as incompressible, so it doesn't really much matter, but let's assume that the pressure is very close to the ambient pressure, so that we don't need pressurized system at the heat source, at this heat transfer fluid system. So the pressure will be 100 kilopascals. And now we had specified the temperature at the point 21, which is the heat source temperature, 200 degrees C, and we had given the mass flow rate of 1 kilogram per second. So 200 degrees C over here. Here it's in kelvins. So now at this first point we can already get the value of the enthalpy, because we have the temperature, we have the pressure, and it's single phase fluid. So we can actually borrow the function, for example, from the subcooled state of the working fluid. And we want enthalpy as a function of temperature, pressure, and the working fluid will change to this incomp T66. Now we don't know anything about the point 22, but for the point 23 we expect this to be the point of the minimum temperature difference of the pinch point. So that means the temperature at this point 23 needs to be, we have the delta T over here, needs to be by the pinch point higher than temperature at the point 2. So let's get the temperature at the point 2 plus the value of the pinch point. Let's get the kelvins. Let's calculate the enthalpy in that point. Now, because we don't have any heat losses in the system, so the heat transferred in certain part of the heat exchanger on the side of the primary fluid needs to be the heat transferred also into the secondary fluid on the other side of the heat exchanger. So it works, for example, between the points 21 and 22 and 3 to 4, or also for the whole heat exchanger, 21 to 24 and 1 to 4. And also this needs to work between the points 21 and 23 and 4 and 2. And these are the points where we have specified the enthalpies, so we can solve the heat exchanger. So the heat transferred from the primary fluid between the points 21 and 23 needs to be the heat transferred into the secondary fluid between the points 4 and 2. And the heat transferred is the mass flow rate of the primary fluid, let's say HS as heat source, multiplied by the enthalpy difference, enthalpy 21 minus enthalpy 23, and this needs to be the heat transferred into the ORC working fluid, so it's ORC multiplied by the enthalpy difference. Now it would be enthalpy 4 minus enthalpy 2. And if we have a look at this equation, so we know the mass flow rate of the heat source, we know the enthalpy difference at the heat source between these 2 points, we know the enthalpy difference in our working fluid, and the only unknown is the mass flow rate of the organic working fluid that we get from this equation. So let's manipulate the variables, and we will get that the mass flow rate of the ORC working fluid is the ratio of the transferred heat divided by the enthalpy difference of the ORC working fluid. Okay, so now we will implement this equation. So the mass flow rate of the working fluid for the organic Rankine cycle is the mass flow rate of the heat source, which here is 1 kg per second, multiplied by the enthalpy difference, enthalpy 21 minus 23, and this will be divided by the difference in enthalpies H4 minus H2. And we get the mass flow rate of the working fluid. Well, of course, in other nodes of the ORC it's the same as here for the heat source. Now when we have the mass flow rate of the organic Rankine cycle working fluid, so we can calculate also the overall heat transfer in this heat exchanger, and the overall heat transfer between points 1 to 4 will be mass flow rate of the, let's do this, mass flow rate at the ORC, and multiplied by the difference in enthalpies H4 minus H1. And then this amount of heat also needs to be the same as the mass flow rate of the heat source, multiplied by the difference in enthalpies of the heat source. That means H21 minus H24. So if we have a look at these two members on the right hand side, so the only unknown that we have over here is the enthalpy H24. So we can get the enthalpy H24, that it will be the enthalpy H21 minus, and now the fraction, this Q14 over here, divided by the mass flow rate of the heat source. So let's now implement this. Let's perhaps somewhere here below, let's put Q heat source, the heat transferred from the heat source, which is the mass flow rate of the ORC times the difference in enthalpies for the heat input into the ORC. So H4 minus H1. The units are kilowatts. And now the enthalpy H24 is the enthalpy H21 minus this Q heat source or Q in divided by the mass flow rate of the heat source, which is 1, and we get the outlet enthalpy 141 kilojoules per kilogram. So now let's convert the enthalpy, or let's get temperature out of it. So again, let's borrow some function for temperature, like this one, and we want to get the temperature out of this pressure, enthalpy, and for this working fluid. And converting to degree C, we get 102, almost 103 degrees C as the outlet temperature from the heat source. So you can see that because of this pinch point within the heat exchanger, we have limited amount of heat we can transfer from the heat source to our working fluid. And if we want the evaporation temperature to be 150 degrees C, so the heat source outlet needs to be at least the 102.7 degrees C. Definitely not less. Now we can also solve the point 22, where it will work similarly, that enthalpy at point 22 will be enthalpy at point 21 minus, and then now we have this part of the heat specified at the ORC, so the heat transferred for the ORC between points 3 and 4, which is the mass flow rate times the enthalpy difference, enthalpy 4 minus enthalpy 3, and this divided by the mass flow rate of the heat source. And again, now we can just copy these two functions over here, and we can see that for this part, for the superheat, it takes just small portion of heat, which is respective to around 4 degrees C at the heat source temperature. Now let's also move further to the heat sink. So we have the points 31, 32, 33 and 34. We can also probably Q in, like heat input into the cycle. Again, let's say that the pressure of the ambient air would be approximately 100 kilopascals. We could also use the standard ambient pressure 101.323, but it doesn't really matter that much here. Now the specified temperature of the ambient air is at the inlet of this air condenser, of this heat exchanger. So it's at the point 31, where the temperature is this 20 degrees C. respective temperature in kelvins. Now, when we will calculate with the humid air, which will be heated up, so the relative humidity is not a suitable variable anymore because it will change, but what will not change is absolute humidity in kilograms of water per kilogram of dry air. So typically the symbol is used omega, and the humid air in the cool probe has a specific syntax, which will be HA probes SI, like humid air properties SI. And if we go to the dialog window for this function, so the output, which we want here, the absolute humidity is W, with the input parameters being, well, first let's put temperature, which we have over here. Second would be pressure over here, and the last one would be relative humidity, for which is used symbol R, and the value is over here. And then in this function we don't have the input for the working fluid, because this function is specifically and only and already given for the humid air. So we get the value of 0.01 kilograms of water per kilogram of dry air. So now this is the parameter that will be constant regardless of the temperature. So now let's get the enthalpy. So the enthalpy will be again function HA probes SI, humid air properties, where we want to get enthalpy based on pressure, temperature, and humidity over here. And let's lock it. And similarly, we could also get the entropy. If we would be interested in that, just change the syntax to S. This was the first point. What else can we do with this heat exchanger? We don't know anything about the point 32 or 34 yet, because we don't know what is the mass flow rate of this cooling air in this heat exchanger. But what we have specified is the pinch point, the minimal temperature difference, which will be here between the point 6 and 33. So the temperature at the point 33 will be temperature at the point 6 minus the specified pinch point. We can convert the temperature to kelvins, and we can use directly the same function as we had before to get the enthalpy, respectively entropy. Now, similarly as we did for the calculation of the mass flow rate of the working fluid in the ORC, so we can also solve the part of the heat exchanger between the points 6 and 8, or respectively 31 and 33. So the mass flow rate, or let's just show it in here, just to make sure. So the Q, let's say 68, needs to be same as Q 33 to 31, And now the Q68 is mass flow rate of the organic Rankine cycle working fluid multiplied by the difference in enthalpies H6 minus H8, and this is the same as the mass flow rate of the cooling air multiplied by the difference in enthalpies H33 and H31. And again, in this equation, the only unknown is the mass flow rate of the air. So the mass flow rate of the air is the fraction with the mass flow rate of the multiplied by enthalpies, marking the heat transfer between 0.6 to 8, divided by the enthalpy difference 33 to 31. But first, we need the enthalpies also to be in the kilojoules per kilogram. So like this. Okay, and now the mass flow rate of the cooling air going through the condenser is the mass flow rate of the ORC multiplied by the enthalpy difference 6 and 8, so H6 minus H8, and this divided by the enthalpy difference 33 minus 31. Enthalpy difference, so here 33 minus 31. And we get the mass flow rate of the cooling air. And now we can express the rejected heat, which is the mass flow rate of the ORC working fluid multiplied by the enthalpy difference, and now it would be 5 to 8. So enthalpy 5 minus enthalpy 8, and the rejected heat is 172 kilowatts. Now, in similar manner as we got the remaining points for the heat source, so we can do the same with the heat sink, with the cooling air. So the enthalpy at point 34 would be the enthalpy, for example, at 31 plus now the all rejected heat divided by the mass flow rate, and for the point 32, so it's point 31 plus now the transferred heat between 31 and 32, which is MORC times enthalpy difference between 7 and 8. And this again divided by the mass flow rate of the cooling air in here. So we have the enthalpies. Now we can get the temperatures out of them. So let's borrow the function for the enthalpy, and now we have function for the humid air, where we want to get the temperature based on pressure, based on enthalpy, and based on the humidity. Okay, we don't need this. and convert to degrees Celsius. Well, what happened here? Again, the enthalpy needs to be in the basic units, joules per kilogram. So you can see that the temperature increase between the points 31 and 32 is really small. That heat for the subcooling of the working fluid is almost negligible. And we can use the same function for the outlet of the cooling air, and now we can see that after heating up from 20 to 30, a little bit more than half of the heat is still more added into the cooling air from the superheating. The temperature goes to 36 degrees. So now we have the heat input, heat output. Well, now let's have a look at work of the expander, which should be the mass flow rate of the RC fluid multiplied by enthalpy difference 4 to 5. H4 minus H5. Similarly, work of the pump. Mass flow rate times enthalpy difference 1 minus 8. And the net work of the cycle is work of the expander minus work of the pump. And we can run a check that it should be also the heat input minus heat output, and the values are correct, so seems like we did not make any mistake. So it was the work of the cycle, the thermodynamic work, and now when we want to get the net work of the system, so we need to include the parasitic load, which in our case will be the required work of the fan. The fan is typically placed at the outlet of the air-cooled condenser, so that would be induced draft fan, which will be placed here at the point 34. And we had specified for the fan that the pressure drop across it is 200 pascals and that its efficiency is 70%. So how to get the required work of the fan? Let's use the definition of technical work, which is elementary change of technical work. dW is VdP. Now the unit volume can be also the unit volume can be also rewritten as 1 over rho as density times Vp. And if we will assume that the working fluid in this case going through the fan is incompressible, so the unit volume or the density will stay constant. Now when we integrate this term, so since the V or rho would be constant, so it would be technical work or unit work of the fan, in our case, will be the unit volume times delta P. And this delta P is the pressure drop, which we had specified as 200 pascals. Now, of course, if we want the absolute value, the work of the fan, So it will be the mass flow rate of the air multiplied by the technical work, which will be this VdP or V delta P, and this term would be the ideal work. Now we had specified the efficiency of the fan, so we have to divide this term by the fan efficiency. Alright, so now we just need to get the unit volume so that we can calculate the work input for the fan. So let's put the unit volume in here. It would be the volume at the point 34. And the syntax goes that humid air properties, HA props SI, now the output would be unit volume, which for the humid air here has the letter V. Eventually we could get also density, which in coolprop, just by the way, has the sign D as density, but it doesn't work in humid air, because in humid air the D would stand for dew point. So it's some kind of like small discrepancy in notation in the coolprop. Anyway, so we want the volume, and the properties which we will use will be the temperature at point 34 at the outlet, then pressure, and the last one will be the humidity, omega or W, which is over here. So now we get the unit volume in cubic meters per kilogram, and we can calculate the work input for the fan. So it's mass flow rate of the air multiplied by unit volume and pressure difference. Now all the units are basic SI units, so the result now is also in watts, the basic units. So we need to divide it by 1000, and this is still the ideal work, and to get the work input we need to also include the efficiency of the fan, and here we have the result in work of the fan in kilowatts. So you can see that actually more than 10% of the work of the cycle is consumed by the fan, which means that's already quite considerable amount. Perhaps some optimization of the condensing temperature and amount of the cooling air could be performed. And anyway, this is quite common in small applications and waste heat recovery, where the auxiliary power input needs to be taken into account. Alright, now when we have the work of the fan, so we can also get the net work of the system, which is just the difference of the work of the cycle and work of the fan. We are not including at this example any electrical efficiency or other self-consumption and parasitic loads. So we get the network output of the system as 21 kilowatts. Now let's put in two more parameters that we will use in a moment. And first will be the heat content of the heat source. Let's call it now as Q heat source. This would be the heat that we could extract from the heat source if we would cool it down to ambient temperature. So that is maximum theoretical heat that can be provided by this heat source. And so it would be mass flow rate of the heat source multiplied by the enthalpy of the heat source inlet and minus the enthalpy of the heat source when it would be cooled down to the ambient temperature. So T equals amp, like this. And also this state T at the temperature, at the ambient temperature, is sometimes called as dead state, and it's denoted with the subscript 0. So let's add here for the heat source one more node, node 0, with the same pressure as above, and at the temperature of the ambient temperature, which was over here, 20 degrees C. And we can get the enthalpy for this point. So there is enthalpy from temperature and pressure, like here. So this function, you can use it over here. And you can see that actually for this thermal oil, the enthalpy, the reference point of enthalpy 0 is very close to 20 degrees C and 100 kilopascals. And now just one last thing, which we will use in a short while. Let's also define let's also specify the entropy at this dead state, at this heat source, at the heat source at the ambient temperature. So now we can get this heat which we could theoretically extract from the heat source, mass flow rate of the heat source times the difference in enthalpies heat source inlet and heat source in the dead state. And you can see that theoretically you could extract almost 340 kilowatts out of the heat source, while you get only 200 kilowatts because of the pinch point limitations and condensation at temperature higher than ambient. And now the last parameter with respect to its heat source will be the exergy flow of the heat source. The Q heat source says how much energy can be extracted from the heat source regarding the first law of thermodynamics, the energy balance. The exergy, on the other hand, says how much of the heat content in the heat source can be theoretically converted to work. So if we had ideal thermodynamic cycle, 0 temperature differences, let's say by limit small Carnot cycles between at each given temperature as the heat source is cooling down, with the negligible temperature difference in the horizontal direction. So how much work this theoretical cycle could extract from the heat source. And how is the exergy defined? The function for exergy starts somewhat similarly as for the energy of the heat source. So let's again start with this. But it's not just the enthalpy difference, but the content of the heat that can be, or energy content that can be converted to work is lower, and it goes as enthalpy at the inlet minus enthalpy in the dead state minus absolute temperature of the dead state in kelvins multiplied by entropy of the heat source inlet minus entropy of the dead state. So it will look like this. So what is within the brackets is the unit exergy, again in the kilojoules per kilogram, and when we multiply it by the mass flow rate of the stream for which we express the exergy, so we get the absolute exergy contents in kilowatts. So let's get the exergy of the heat source stream in here. So it will be the mass flow rate of the heat source multiplied by now enthalpy at the inlet minus enthalpy in the dead state minus now the temperature of the dead state in kelvins multiplied by entropy of the inlet minus entropy of the dead state. So this, on the other hand, says that even though the amount of heat in the heat source is 340 kilowatts, so we could not make by any means more than 78 kilowatts of electricity if the ambient temperature is at 20 degrees C. Okay, now let's have a look at efficiency, or various expressions of efficiency. So first, the efficiency of the cycle. It's the work of the cycle divided by the heat input. Now we can also have the net system efficiency with respect to the heat input. So it would be net work divided by heat input, and you can see 1.5 percentage point lower just because of adding the work of the fan, or almost 10% lower. Now we can also express the efficiency with respect to the heat content in the heat source. So it's so-called utilization efficiency. So this utilization efficiency is the, well, let's have it as utilization efficiency of the cycle. So it would be work of the cycle divided by the, and now Q heat source, the heat content in the heat source. So it's only 7% compared to the work of the cycle. The utilization efficiency is obviously lower because there is still large portion of the heat which is not used. Now if we have utilization efficiency of the whole system, let's call it net. So it will be the net work divided by the, again, the heat content of the heat source, and it's just 6.2%. And now let's have the Exergy efficiency. We can also express the Exergy efficiency just for the cycle. So it would be work of the cycle divided by the Exergy of the heat source. And we can see that the cycle could convert the heat content in the heat source with respect to the second law of thermodynamics, with respect to the thermodynamic limits, by 30%. So less than 1/3 of the theoretically obtainable work can be received from this cycle, and it's just the cycle. And of course we can also define the Exergy efficiency for the whole system. So it would be the network output divided by the Exergy of the heat source, and it's almost 27%. So this last value, the net Exergy efficiency, is the parameter that tells us how well the system can convert the thermodynamic potential in the heat source into the work. Okay, now let's draw the QT diagrams and TS diagram of the cycle. So let's start with the QT diagrams, and let's have here the points 1 to 4. Here will be the heat transferred in units kilowatts. Here we will have the temperature of the working fluid, and temperature of the heat source. Now this point 1 for the working fluid is respective to the point 24 at the heat source. This point 2 is also as point 23. Point 3 is corresponding to point 22, and point 4 corresponds to point 21. Now the heat transferred in the heat exchanger will start at 0, and then we can choose whether to use the heat source or the working fluid. So here, as I go 1 to 4 with the working fluid, so I will use that. So mass flow rate of the working fluid times enthalpy at the point 2 minus enthalpy at point 1. And let's lock the cells like this so that we can just extend it. And also here we can check that the heat transferred in the heat exchanger is the Q in. Same would need to work also if this would be the mass flow rate. So let's just check here. Mass flow rate of the heat source times enthalpy at 23 minus 23 here minus enthalpy at 24. So you can see this can work as some kind of check that the values are correct. And now the temperatures. So the working fluid, it's temperature 1, temperature 2, and 3 and 4. And for the heat source, temperature 24, 23, 22, and 21. Now we can take these values and let's put in a scatter plot. Let's get it into some nicer shape. And as we have the data row for the working fluid, so we can also get the second data row for the heat source. Okay, so we can see that the temperature heat diagram indeed looks like what we have, kind of like what we have drawn illustratively in here. Just you can see the really relatively low result of the low specific heat capacity of the working fluid in comparison to the heat of evaporation. So this preheating part is much longer than, for example, what you could expect for water. Okay, so now we can do the same thing as we did here, also for the heatsink. So we will have Q out, temperature of the working fluid, and temperature of the heatsink of the air. And here the points will be, well, now let's start, for example, from the point of the air. So it would be 31, which is corresponding to point number 8. then 32 corresponding to point number 7, 33 corresponding to 6, and 34 corresponding to 5. So the heat transfer will start again at 0. The first point, mass flow rate times difference in enthalpies, enthalpy is 32 minus enthalpy is 31. And again, let's log the 31 and let's log the mass flow rate. And again, the overall heat transfer in the heat exchanger is the rejected heat. And same would also work for the same values need to be received for the mass flow rate times enthalpy difference between, for example, 7 and 8, 6 and 8, and 5 and 8. Now the temperature of the working fluid at the point 8 over here, then temperature 7, 6 and 5, and temperature of the air at the point 31 to 34. Now let's use the graph as we had in here, and we can just transfer the values, or sorry, we can just transfer the ranges of the data sources. I put there twice the same, so now so again you can see that the shape of the temperature heat transfer diagram looks similarly to what we have expected. And again you can see that as a result of the large superheat of the working fluid after the expansion, so there is this large portion of the superheating before the working fluid gets to the condensing temperature of 40 degrees C. So there is actually quite significant potential for adding a recuperator, which would save some heat input. And we will explore that in the last part of this tutorial. Now let's draw the temperature entropy diagram of the cycle. So first, for example in here, so first we will draw saturation curve of saturated liquid and vapor. So let's put in 3 columns, entropy of saturated liquid, entropy of saturated vapor, and temperature. Now let's have the temperature going from, let's say, 20 degrees C up to, well, let's put in up to 240. And now, or let's go to 250. Now the entropy of the saturated liquid, so I will just borrow the function from here. Where we want the entropy based on the temperature, for which we will use the cell over here, and the quality, which for saturated liquid is 0, and for our working fluid. And of course the temperature has to be plus 273.15 to have the basic SI units. Right, so it's temperature of saturated liquid. Then let's get temperature of the saturated vapor. So again, from the same temperature, just the Q would be 1. And let's expand these functions across our range. And now let's see what happened here. At the 250 degrees C, the functions return error instead of value of the entropies, and it will be most likely, as we will see in a while, because it will be already above the critical point. So let's try 245, and there we still have valid values. So let's draw a diagram from these values. I will again use this as kind of a template. Now the x-axis, saturated liquid, y-axis, and let's extend the values. And then let's get the second line. Well, yeah, you can see that I switched the axis, so let's just do it this way, and this one. Sorry, that's both saturated liquid, so now one for saturated vapor. Alright, still a little bit improve the format. So let's go from minus 0.5 up to, let's say, 0.8, maybe 0.9. Now the crossing of the y-axis at minus 0.8. And also let's get the better looking curves for in the diagram. So like this. So we have the temperature entropy diagram for our working fluid. And you can indeed see that at the highest temperature that we have, 245, we are nearly at the critical point. And now let's add the values for our thermodynamic cycle. So we can go to select data and add new data series. So the first can be, for example, the pump going from point 8. So the going from point 8 to 1. So the x-axis is the entropy, so entropy 8 and 1, and y-axis is the temperature 8 and 1. Next one is the preheater. So the values go from 1 to 2, entropy 1, entropy 2, temperature 1, temperature 2. Following is the evaporator, which goes 2 to 3. Then superheater, 3 to 4. Following on that is the expander, which goes from 4 to 5. And the x values also need to be 4 and 5. Now we have the Preheater, 5 to 6. Condenser, 6 to 7. And the last is the subcooler, 7 to 8. So now let's see how it turned out. Well, something happened with the Preheater. Let's just check. Yeah, I used enthalpy instead of temperatures, so Preheater 3 to 4 goes like this. Have the legend fitting into the space, and now we can see the whole cycle in the TS diagram, where, well, you cannot really see the pump unless you would zoom in really very closely. Then the preheating, evaporating, superheating, then is the expander, the superheating, condensing, and subcooling. Now we will have a look at sensitivity analysis of the cycle parameters and also do some optimization out of it. So let's copy the cycle parameters that we had here somewhere where you have space, and copy it just as values. Well, let's use it. Let's do it like this. And let's have the temperature range from, let's say, 90 degrees C to 180. So probably we will need to move this diagram over here. Okay, and now we will be varying the evaporation temperature. This will be the EVA from 90 to 180 degrees C, and we will see how the cycle parameters will change. So first, let's change the temperature of the evaporation from 150 just to 90 degrees C. And also let's relax the limits of the diagrams. And what you can see here is that we expected the pinch point, the minimum temperature difference, to be at this point, but if we decrease the evaporation temperature this low, so the minimum temperature difference would be here at the outlet of the heat exchanger, and we can indeed see that the temperature at the outlet over here is 40 degrees C, while the temperature at point 1 is 35, so the temperature difference 10 degrees C would not be justified. So in this case, we would need to modify the model with expectation of the minimum temperature difference in here and recalculate the cycle. That's beyond the available time in our tutorial. So let's just see what happens if we increase the temperature to 100 degrees C. And at this point, 10, 100. Okay, so now we have 35 and we have 45.3, so this condition is at the outlet just valid. We can see that the lines go nearly parallel and the cycle can work within our boundary conditions with this model as we built it. Also, you can see the kind of like narrower cycle in the TS diagram, and let's get the results for the system, cycle and system, and copy it to 100 degrees C just as values. So now let's increase our temperature step by step and get the values of the cycle and system. If you would be doing this with some more, let's say, complex model and multiple times, so it might be feasible to write a macro for this, but if you're using just a few values, so it's faster in this way by hand. Okay, so now we are at 180 degrees C, and the interesting thing that happens here is that the functions for the heat source will not be working, but this is just anomaly that happens for this specific working fluid at this temperature. Well, since CoolProp is free software, so it might have some glitches. You can see that 179 would work, same as, for example, 181. But now if we would use 181 degrees C, so the temperature at the point 4 is 191, and we would not have justified the minimum temperature difference already at this point between the heat source and the superheated vapor. Not to mention that for the superheated vapor the heat transfer coefficient is significantly lower than for the for the liquid, or especially for the evaporation. So this case would not be possible, but 179 would be okay. And the 180 degrees C is basically a limiting case within our boundary conditions for this system. So here is 179. Alright, so now we have the results for our system in the range of evaporation temperature from 100 degrees C to almost 180. And let's have a look how the cycle efficiency behaves. So as you can see over here, the efficiency of the cycle is increasing as the evaporation temperature increases. That's because it's just the thermodynamic cycle, and of course it's based on the second law of thermodynamics. Higher temperature difference in the cycle, higher mean temperature difference of the heat addition and heat rejection results in higher efficiency. So by this you could say that increasing the temperature of the evaporation would be a good thing. But now let's put aside a new graph where we will have a look at the work of the cycle. And suddenly you can see that the shape of the curve of the work of the cycle is completely different, where with the temperature of evaporation it's first rising slightly, going into some point of a maximum, and then decreasing. Why is this happening? Well, let's have a look at the heat input into the cycle. Where with the lowest temperature you could see that the lines of the temperature profiles of the liquid being preheated and of the working fluid were basically parallel, so we could extract really a lot of heat out of the heat source, almost 300 kilowatts, where the maximum theoretical content is 340. But with this amount of heat that we extracted from the heat source, we converted it to work with only about less than 9% efficiency. Then, as we increase the evaporation temperature, so the heat content the heat extracted from the heat source is decreasing, but the efficiency is increasing, and that's up to the point of this sweet spot. Where there is the maximum work of the cycle over here. So this maximum work of the cycle is also corresponding to the maximum point of the cycle utilization efficiency. You can see that the maximum was about 120 degrees C, maybe just a little bit behind that, same as with this curve. Sorry, therefore now it's cycle utilization efficiency, and really the maximum point is over here. Now let's have a look at the network output. The fan power is increasing as the heat extracted from the heat source increases. That means also more heat needs to be rejected. So the maximum of the net power output is at temperatures just a little bit higher than for the gross performance of the cycle. We can see also the work of the fan. Let's put it at least to the secondary axis. That work of the fan is indeed decreasing because the amount of heat that needs to be rejected is decreasing as well with the temperature. So now with the efficiency, let's also have a look at the net efficiencies. So we can see that the net efficiency of the cycle is a little bit lower because of the fan, and that the net utilization efficiency, which is also a little bit lower, has the maximum at little bit higher temperatures, same as the network output. And now the last parameter that we will have a look at will be the Exergy efficiency. like this, and the net Exergy efficiency over here. And let's have a look at the points of the maximum of Exergy efficiency. And we can actually see that the Exergy efficiency of the system has the maximum point at the same temperature as is the utilization efficiency and as is the work of the cycle, while for the net values, the net Exergy efficiency has the maximum point at the same place as the net utilization efficiency and net work of the system. So these are the general characteristics that can be basically applied to most of the waste heat recovery systems. Now, in the last part of this tutorial, we will explore the impact of adding the Recuperator into our cycle. So you can see the process flow diagram up here in the right upper corner, where compared to the original layout, we added this heat exchanger between the outlet of the turbine and beginning of the set of the heat exchangers for condenser, and outlet of the pump and beginning of the set of heat exchangers for evaporator. So what does this heat exchanger do? As the outlet of the expander is superheated steam at quite considerable temperature. Well, when we take the previous example over here, at 179 degrees C it's 145. If we take the optimized case for about 120 degrees C of the evaporation temperature, still the temperature of the outlet of the expander is 104 degrees C, which is still quite significant potential to do something with that. So part of this heat, when this vapor is cooling down, is taken from it, from the 0.5 to 0.5 recuperated over here, and it's transferred to the cold fluid after the pump before the heat input into the cycle. So since this vapor being cooled down is single phase fluid, and also subcooled liquid after the pump is also single phase fluid, so the temperature profile will look somewhat like this. It would be straight or eventually just slightly curved lines, but no processes like phase change would take place. Now the question is if the minimum temperature difference would be over here at the cold side of the heat exchanger or here at the hot side of the heat exchanger. The answer to that question lies in the fact that the vapor, the gaseous phase, has always lower specific heat capacity than the liquid phase, or almost always. So that means for the same amount of heat transfer, which is the same for the both sides of the heat exchanger, the fluid with the lower specific heat capacity will undergo higher temperature change. So this line will be steeper, while the liquid fluid with the higher specific heat capacity will undergo lower temperature change over here. So it translates in the fact that the minimum temperature difference has to be here at the low temperature side of the heat exchanger. Now what will be the impact of the recuperator at the heat input and heat output? So we save some of the heat from the heat input from the preheater. So basically we cut off the left part of the heat exchanger in the QT diagram, because after the recuperator the liquid working fluid is at higher temperature, so that does not extract so much of heat from the heat source. And similarly, since we get rid of some of the heat already before starting of the condensing heat exchanger, so in the superheater part we cut the bit of right side of the QT diagram, so instead of the 0.5 the heat rejection will start at the 0.5 recuperated, and on the side of the cooling air its outlet temperature will not be that high, but it ends up lower. Still we have limitation of the heat transfer by the pinch point between points 6 and 33, or for the heat input between the points 2 and 23. So now let's do the modifications to the cycle to update it to the recuperated layout. For that, I recommend you to copy the model of the cycle, for example, to a new sheet, so that you can still have the previous one, and then we will compare the differences. So we have 2 additional points compared to the previous case, point 1 recuperated and 5 recuperated. So let's add them into our layout, into our table. Here will be 1 recuperated, and over here will be 5 recuperated. Now we don't again assume any pressure drops, so the pressure at 1 recuperated will be same as at point 1, and 5 recuperated will be same as point 5. And since we expect the minimum temperature difference to be at this point, between 5 recuperated and 1, we can get the temperature at the 5 recuperated by using the temperature at point 1 plus the minimum temperature difference. So now we have temperature, pressure, the working fluid is in single phase, so we can get enthalpy and entropy from that. So let's get the temperature in degrees Kelvin, and for example here at point 8, the temperature and pressure, the enthalpy and entropy are functions of pressure and temperature, so we can use these 2 functions. So now we have the enthalpy at the point 5 recuperated, and from that and knowledge of the mass flow rate, we can get the recuperated heat. So let's add this over here, Q recuperated, which will be in kilowatts, and it will be the mass flow rate of the ORC working fluid multiplied by enthalpy difference 5 and 5 recuperated. So we can see that almost 70 kilowatts will be saved from the heat input into the cycle, and the same amount will be also saved from the heat rejection. Now we can also get the point 1 recuperated from the balance of the heat exchanger, where the point 1 recuperated needs to be the point 1 plus the enthalpy increase, which is the recuperated heat divided by the mass flow rate. Now we could also exclude using the mass flow rate from our calculation, because on both sides of the heat exchanger there is the same mass flow rate, so the calculation needs to also work as enthalpy at the point 1 plus just the enthalpy difference between point 5 and 5 recuperated. So it would be like this, and you can see that we would get to the same value. Now we can get the entropy from the pressure and enthalpy, and also from the pressure and enthalpy we can get the temperature. And we can see that by adding the recuperator, the working fluid can be heated up from 35 degrees C from cold state after the pump to 83 degrees C already before it enters the preheater. And also you can see that 83 is more than 10 degrees C, lower than the 104. So the assumptions of lower temperature difference at the low temperature side of the heat exchanger was valid. And just for the purposes of clarity, let's highlight the added nodes and parameters in our model. Now let's go to the heat source and heat sink. First, at the heat source the point 24 shifted, so there will be difference in these values. Where the enthalpy at the point 24 is calculated from heat input. Heat input is another parameter that obviously changed, because now it is not difference between points 4 and 1, but 4 and 1 recuperated. So now we get the heat input after recuperation, and as you can see, instead of previous 61 degrees C at the outlet of the heat source, now the outlet of the heat source is at 100 degrees C. Similarly, it will go with the heat rejection, where the point 34 shifted to lower temperatures. So it's the point 34, where the enthalpy is calculated from the rejected heat. So it's another point that changes, because the rejected heat is now not the difference between points 5 and 8, but 5 recuperated and 8. Like this. Now for the rest of the parameters, they will stay basically with the same functions. Nothing changed to the inlet and outlet of the expander or the pump, so that remains the same as work of the cycle. Function for the work of the fan is related to the volume over here, automatically calculated from the outlet conditions. Heat input, the heat content in the heat source or exergy content in the heat source stay the same, as nothing changed to the temperature or mass flow rate of the heat source. And then we will compare all the parameters with the non-recuperated case in a short while, after we fix the QT diagrams. Now for the QT diagrams, it's the first part over here, it's not anymore between point 1 and 24, but 1 recuperated and 24. Then 223, 322 and 421 stays the same. And with the heat transfer, the first part between points 2 and 1 recuperated needs to be corrected. And with that, also the other points of the heat transfer will be referring to the 1 recuperated case. Now with the temperatures, again the 1 recuperated is used instead of 0.1, and the rest remains the same. The links here for the heat source are still valid. So you can indeed see that for the heat input QT diagram, we cut off the left part, and the heat source outlet is now at significantly higher temperature than before. Now for the heat rejection, so it remains quite similar up to the point 34.5, where now it will be 34 to 5 recuperated. The heat transfer is now in this case referred to the heat sink, so it's in correct form. Overall heat transfer is over here, it's correct. And for the working fluid, the low temperature parts are still the same, just instead of the 5 we need to use the 5 recuperated. And here we have the fixed QT diagram for the heat rejection, where again we cut off the right hand part of the diagram and we lowered down the rejected heat into the environment by the cycle. Okay, now let's compare the values with the recuperated and non-recuperated state. So this is the recuperated, where we have the evaporation temperature 120 degrees C, and here we will get the values of non-recuperated. So let's also put here in the original model 120 degrees C, so that the boundary conditions are the same, and copy the values. Or we actually don't need to copy the values directly, we can just refer to them. Then you could also link together the temperatures and have immediately the comparison of both systems in single sheet and interactively. Okay, so now let's see the difference between the non-recuperated and recuperated system. Heat input and rejected heat both are lower by the recuperated heat in the recuperated case, which translates into higher cycle efficiency, but the work of the expander, work of the pump, and work of the cycle remains the same. The work of the fan is slightly lower for the recuperated case, but this very small difference is caused only by the lower temperature at the cooling air outlet and therefore lower unit volume. But practically this difference is almost negligible, so the network output is nearly the same. Now for the heat source, both for the energy and exergy content, well, we did not do anything to the heat source, so these parameters remain the same. As I said, the cycle efficiency increases quite considerably because we have much lower heat input, but the utilization efficiency is the same. The very slight difference in the net utilization efficiency is caused by the very slight difference in the fan work. And now for the exergy efficiency, again, we did not do anything to the heat source. We have the same work of the cycle, so we have the same exergy efficiency of the cycle. Slight difference in the net exergy efficiency, again due to the fan. So you can see that adding a recuperator into our system increases the efficiency of the cycle, but in case of waste heat recovery, it does not increase the work output or the network output very negligibly. So for this reason, unless you have some limitation on the temperature of the heat source outlet, for example due to some precipitation of minerals in geothermal applications or condensation of flue gases in application to some gaseous waste heat, so adding a recuperator into such systems is generally not justified. Okay, so that's all from our tutorial on the organic Rankine cycle. Hope you liked it and hope to see you at the next one.